Hi, I'm Alex Richter, and I will be exploring the electric field effect in atomically thin carbon films from 2004. So, the field of electronics is centered around applying a voltage to a material and utilizing and manipulating its electronic properties in order to offer the most utility in a specific situation. So, um, electronics range from Bluetooth speakers, computer speakers, all the way to iWatches and even like remote control robots. So I've defined the electric field effect, which is um, basically the main phenomenon behind changing current and carrier concentration of a material in order to vary the electrical output of it as a semiconductor. So from being the main semiconductor conductive material in the field for many years, um, silica as an electronic has been researched and perfected extensively and is near its maximum output. This is part of what has led researchers to searching for new materials to be semiconductors and has led to the discovery of graphene's utility. Um, uh, because of this, uh, two-dimensional materials are most commonly used for nanoelectric devices. It's because of the ease associated with fabricating them into larger, more complex structures. So metals are common for employing the electric field effect manipulations on, but they're required to be very small in order to reduce the energy and utilization of higher frequencies necessary to make them a useful semiconductor. Metals are a sea of electrons, so they're very dense populations of electrons retard the penetration of external field that's applied to the material. Therefore, that's why they must be so short in length, because the electric field can't penetrate very far. In semiconductors, though, there's a lower density of electrons, which makes it possible with holes to induce the electric field further into the material. The penetration of electric field changes the conductivity of the semiconductor at the surface of the material, and this phenomenon is referred to as the field effect. So in the search for new semiconductor material, graphene has been in the spotlight because of its attractive electronic properties as well as its atomically thin characteristics, which are necessary because the electric field is screened at very short lengths and bulk carrier concentrations in semiconductor metals, and they're much greater than the inducible surface charge of the field effect. Graphene is also unique for having these excitable quasi-particles native to it called Dirac electrons, and they're noted to have a vanishing of carrier mass associated with them at a specific Dirac point. This vanishing of carrier mass induces a magnetic oscillation that gives graphene some of its unique properties. So, graphene has been studied in excess of 60 years, but was not found to be freestanding and stable until 2004, which revived its presence and hope in the scientific field. In 2004, just a rundown of some things that happened. The cost of gas was $2.10. Average cost of a home was $274,000. The Red Sox won the World Series for the first time since 1918. Martha Stewart was convicted of a felony and sentenced to 5 months in prison, and it was the 60th anniversary of D-Day. Because of the observation that graphene's low melting point decreases with decreasing thickness, the stability of graphene was thought to be minimal, and therefore scientists had to produce 2D graphene films that were on 3D hosts, such as monocrystals or had identical crystal lattices. These served as foundations to support the unstable graphene, but has a two-dimensional honeycomb carbon sheet. It can be made into fullerenes, nanotubes, or actually even 3D structures, as I'll show you in a further slide. So here, just an example of a 3D graphene structure is shown. After confirming that the charge carriers of graphene were indeed massless quasi-particles, noted as Dirac fermions, it entered the spotlight as a material to be studied intensively. Graphene contains Dirac-like excitable electrons which give the single-layer carbon allotrope some unique features. Dirac electrons are quasi-particles, and acknowledging them allows one to take into account crystal lattice interactions that may be observed in graphene. Dirac electrons can be thought of as electrons with no resting mass or neutrinos that have gained a negative charge. Graphene's unique properties arise from electron hole degeneracy and the disappearance of carrier mass at the neutral point of this material. The vanishing mass surrounding the Dirac or neutral point produces magnetic oscillations and is a unique feature attributable to the fictitious quasi-particles, Dirac electrons. Extremely thin films tend to be thermodynamically unstable and discontinuous if they are only a few nanometers thick, and under these conditions they're not even found to exhibit the field effect, so they're useless. Against these observations, graphene has stood alone as the only few-layer graphene film to exhibit the field effect, even though it's very thin, even on the scale of a few nanometers. The few-layer graphene has been found to be even slightly metallic in nature and continuous at standard conditions. It's argued that the stability of 2D graphene can be attributed to its extraction from 3D graphite, which I'll show you in a few slides later, in which very strong interatomic bonding and microsizability reduce the effects of thermal fluctuations, such as dislocations and other defects that would make it discontinuous and thermodynamically unstable. So, just to recap, because thin films are thermodynamically unstable and discontinuous, they don't exhibit the field effect. Graphene is unique for being continuous, though extremely thin, on the scale of a few nanometers, even when stacked more than one high, yet it still exhibits the field effect. So this was interesting and led the researchers to continue their research and explore the electronic properties of graphene. So graphene, for its admirable qualities, has been added to some materials, and in addition, other materials with their admirable qualities have been added to graphene before to make composites that yield the admirable qualities of both materials. Graphene has been added to copper in some cases to increase its tensile strength and retain the desirable electronic properties of both materials. Graphene has also been added to silica in some applications, such as for coating silica to serve as a filter of aromatic pollutants in water. In addition, graphene-coated silica balls have even been shown to have a fast charging time, and this was exemplified in lithium rechargeable batteries. One example of how reduced graphene oxide has been added to copper was to put the graphene oxide on top of the copper to increase the desirable electronic properties. Graphene has many applications, some of which have not even been discovered yet, though most recently in October 2017, graphene has been explored further for its potential to advance scalability and feasibility of radio frequency gas sensors. This came after it was found to be the first monolithically integrated complementary metal oxide semiconductor. This was the graphene sensor. This work and many other outlets of potential applications of graphene will be explored in the future, I'm sure. This research paper will explore the success of graphene as a conductive material while manipulating the electric field effect upon it. So the researchers in the paper I read sought to analyze the electronic capabilities of graphene while manipulating the electric field effect upon the material. They began by harvesting a film of graphene from a raw graphite sample. They did this by mechanical exfoliation of pyrolytic graphite, which in everyday terms is just repeated taping and peeling of the raw graphite and producing a film that can be deposited on a substrate, in this case silicon oxide. So here's a diagram showing the graphene film deposited on a silicon dioxide substrate. Here's the graphene silicon dioxide substrate. To this, metal contacts were added, and in addition, a multi-terminal Hall bar device. The remaining components were added in order to make a device called the multi-terminal Hall bar device that was able to have a gate voltage applied to it and electronic output measured from the device. Here is a scanning electron microscope image from the original research paper, showing what is shown in this computer-generated diagram. Here's the graphene film deposited over a silicon dioxide substrate with the Hall bar device shown in the middle in a cross section. So on this page, the electronic data output derived from the multi-terminal Hall bar device is shown. It's to be noted first that there was unintentional p-doping from water. This was not expected, but it shifted all the data rightward as far as sheet resistivity, conductivity, and the Hall coefficient go. The researchers advised to put the multi-terminal Hall bar device in an annealed vacuum in the future, and they found that this reduced the effect of p-doping due to water's presence. Sheet resistivity is noted to reach a maximum at a positive gate voltage because of this shift. Shown are 5, 70, and 300 Kelvin. Moving on, conductivity's dependence on sheet resistivity can be noted due to its shift rightward into positive gate voltage region. Because the sheet resistivity was shifted, conductivity was also shifted, and the sign change of the Hall coefficient was shifted from the origin. It's to be noted that conductivity varies linearly with applied gate voltage. In addition, the Hall coefficient experiences a discrete sign change at the gate voltage at which sheet resistivity reaches a maximum. The data for Hall coefficient shown is for 5 degrees Kelvin. Moving on, the carrier concentration's dependence on temperature is shown to be linear by this data. The data trend can be explained by the model of overlapping conductance and valence bands in a 2D metal. Basically, this experimental quantitative data can be explained by a two-dimensional metal with no band gap existing. So applying a gate voltage induces surface charge density, which shifts the Fermi energy value. The permittivity of free space, the permittivity of silicon dioxide, electron charge, and thickness of silicon dioxide play a part in this. The surface charge density was found to be 7.2 times 10 to the 12 inverse centimeters squared for a gate voltage of 100 volts. This is a high surface charge density for graphene and exemplifies its electronic potential. Electric field doping transforms the small overlap of graphene into either a sole electron or hole-only conductor through a state of either, number 3, mixed holes and mixed electrons. These 3 regions of electric field doping are observed in the data. Sole electron and hole-only regions exhibit a Hall coefficient that decreases with increasing carrier concentration in the typical form. The Hall coefficient is proportional to 1 over NE. The resistivity is proportional to 1 over NE mu. However, in the state of mixed holes and electrons, sigma conductivity changes insignificantly with gate voltage, which indicates a carrier substitution while Hall resistivity reverses its sign, exemplifying its proportionality to the difference in density of electrons and holes. With no gate voltage or electric field doping, few-layer graphene acted as a whole metal due to unintentional water doping, which, like I talked about, causes shift to the right. In an annealed vacuum, they found that it could be shifted leftward. Researchers believe that the intrinsic few-layer graphene is a mixed carrier semiconductor because water exposure led to p-doping, yet ammonia doping led to n-doping. Carrier mobility is determined from field effect, and magnetoresistivity ranged from 300 to 10,000 centimeters squared per volts times seconds. This was found to be independent of absolute temperature, therefore indicating the limitations imposed by scattering. The average free path was 0.4 micrometers, and the high carrier mobility is consistent with previous studies in which intercalated graphene with charged dopants in close proximity to graphene resulted in high carrier mobility as well. So the 2D nature of the charge carriers in few-layer graphene was proven by quantifying the homogeneity and quality of the material through a process of keying in on Shubnikov-de Haas oscillations in longitudinal resistivity and Hall resistivity. Measurement of these oscillations from a multitude of angles between the magnetic field and graphene films displayed a dependence only on the perpendicular component of magnetic field, which is consistent with the 2D model that we talked about earlier for the two-layer metal with two-dimensional metal with no band gap. The linear dependence of these oscillation frequencies shows that Fermi energies of holes and electrons is dependent on concentrations of them, thereby proving the 2D nature of the charge carriers. It was also found that band overlap decreases with decreasing number of graphene layers. Theoretically, a single-layer graphene substrate is a zero-gap semiconductor, so the fact that band overlap decreases proportionally with the number of graphene layers agrees with this. In discussion, like we talked about earlier, the large surface charge density and the high carrier mobilities make graphene a highly suitable material to perform as a metallic transistor. Also due to its ability to be micro-sized, its ballistic transport, and its linearity of current voltage qualities, and even further, its ability to sustain very large currents, graphene is highly suitable for applications in electronics. The limited on-off resistance ratio of the material is a limiting factor, but that's a limiting factor of any material without a band gap greater than Kb times T. But it can be increased by using P to N junctions or local gates and even point contact methods. In exploring the applications of graphene, some challenges are faced. One of them is trying to introduce a band gap to the material alone. So introducing a band gap to graphene as just graphene with no other composite materials involved. Also producing large graphene films will offer some resistance, as we'll see, and producing well-defined widths and clean edges on nanoribbons is also a challenge faced in the field. Production of graphene on a microscale produces very small single-layer allotropes of carbon that retain all the desired electrical and mechanical properties as conductor. Yet on a larger scale, the desired properties can be very hard to preserve. When produced in large sheets, graphene films offer noticeable resistance that hinder and decrease its potential output and efficiency as an electrical conductor. Researchers have developed a process of transferring graphene film, like we saw earlier in the experiment in the visual that had mechanical exfoliation with the tape. They've been able to transfer the graphene film to a silicon dioxide substrate at low temperature, which preserves the electron mobility of the material and therefore efficiency as well. Researchers have found that incorporating graphene film into composite materials also allows one to better capture and utilize the admirable electronic characteristics of graphene. When hosted by a composite material, graphene can be more easily tuned to meet the experimentalist's applications. We saw this when it was added to copper to retain the electronic properties of graphene and the tensile strength of copper. In addition, a polystyrene graphene composite was manufactured with a very low percolation threshold and sufficient conductivity to perform its electrical applications from two very inexpensive materials, polystyrene and graphene. You may recognize polystyrene from styrofoam cups. A band gap is required for transistors and electronic applications, yet pristine graphene has no band gap like we talked about. Introducing a band gap to graphene by manipulation and fabrication reduces the mobility as an electron carrier. Monolayered molybdenum disulfide produces high mobility, high current on-off ratios, and minimal waste of power when on standby. Monolayered molybdenum disulfide has a direct band gap and has been proposed to complement graphene in applications such as optoelectronics because as a very thin and transparent semiconductor, it's possible to do this. It is possible to introduce a bandgap to graphene, but it stresses the material and ends up reducing the mobility to that of strained silica. So what's the point of introducing a bandgap to graphene if it's just going to be as poor as silicon was in the first place, which is why this research even started. Shubnikov to Hawkes oscillations have been observed in high mobility monolayer and multilayer molybdenum disulfide, therefore exemplifying the 2D model that the material follows because the oscillations depended only on the perpendicular component of magnetic field. Molybdenum disulfide has been experimentally analyzed for its applications in water-related environmental applications, such as contaminant absorption, disinfection, and even membrane-based separation, among other processes. Moving forward, it has been proposed that graphene can be made into a powder for electric batteries and will be useful because of its large surface to volume ratio in combination with high conductivity that improve the efficiency of batteries. Another application of monolayer graphene, this time is for trapping biomolecules by dielectrophoresis, and this is made possible by its generation of single electric field gradients. Graphene is able to be used like tweezers for trapping biomolecules when it's atomically thin and attached to the end of a substrate, sort of like tweezers, where graphene would be the tip. In the realm of smart materials, a very interesting field, materials have been materials that reversibly respond to chemical, electrical, light, and temperature, or even mechanical stimuli. Graphene has been entering this field of smart materials. This is because graphene offers strength, cheap production, and stability over polymer-based smart materials, which have previously dominated the field. Chemically modified graphene offers great potential towards the future of high-performance smart materials because of how easy it is to process it into films, fibers, porous frameworks, all to meet the needs of the material, of the researchers' expectations as well. So I hope my applications are interesting. I hope you enjoyed my presentation on atomically thin graphene films and the electric field effect. I'd like to thank my professor, Haitao Liu, my classmates, the University of Pittsburgh. Here are some references I use specifically in this paper, and thank you for watching.